So welcome, this is another lecture in continuation on topology on the topic separation axiom. We have till now 9 videos and this is the 10th one, and now we will do some more theorems on regular spaces. So the first theorem what I am going to prove today, the theorem is prove that R is the set of real numbers with usual topology is a T3 space. This is T3 space, this we have to prove. And how the proof will go. First let us see how the proof will go. This is R, the real line. And what we will do, I am first giving out the outline and then we will move on to the proof. So we will take one closed set. In particular I am taking a closed interval. So it is a closed interval, say F, and I'll take a point X here. I'll take a point X here which is not in F. Since X is a point which is not in F and F is closed, so definitely there will be a neighborhood. X is not a limit point of F, so there will be a neighborhood. That means an open interval, you can say X minus epsilon, X plus epsilon. This type of interval will be there, such that its intersection with F is phi. This will definitely happen. Now we will proceed further. How to move on to the final step. So what we will take, I'll take one open interval with center at the point X and radius, or you can say distance from the center point of both sides, as epsilon by 3. So this I'm going to take as, this point is X minus epsilon by 3, and here I will take X plus epsilon by 3, and this interval, this open interval, I will name it as you can say G. On the other side, what I will do, in the closed set F, there are infinitely many points. For every point here in this interval, I have just illustrated some of the points. In fact, there are infinitely many points. For every point, I will take, suppose for this point, I will take this interval, open interval. If this point is y, I will take y minus epsilon by 3, y plus epsilon by 3, and open interval, this one. So this will cover this portion. Similarly, for this point, this is y1. Say this is y2. For y2, once again, I will take this interval, that is y2 minus epsilon by 3, y2 plus epsilon by 3. This interval I will take. And similarly, for all points, for this point again, for this point again, this open interval may come outside of this closed set. So if there is some point here, your interval will be looking like this. If this point is there, your interval will be looking like this. And now what I will do, I'll take union of all these open intervals. So union of all these. So I'm not writing here y1. Generally you can say y, where y is an element of F. So this set, I'll name it as H. Since for every point of F, I have one open interval, y minus epsilon by 3, y plus epsilon by 3, definitely their union will cover the whole set F. So what will be there? That F will be a subset of H. And X is the center of this open interval, so definitely X will belong to G. Now X will belong to G. Y, F is covered by H. G and H are open sets. Now the only thing that remains to be proved is that G intersection H is phi. And once I will prove G intersection H is phi, what the result finally I have obtained. I have taken one closed set F, a point X not belonging to F. I have obtained two open sets G and H, G containing X, H covering F, and their intersection is phi. That makes the space regular. And already in a previous video you can see you have proved that this RU is a T1 space. It is regular, it is already T1, and regular plus T1 means T3. So this RU will become a T3 space. But this is just outline. Now I'll move on to the proof. How to prove it. So this was just an outline. Diagrammatically proof you can say. Now we'll move on to the analytical proof. So let F be a closed subset of R and X be a point not belonging to F. Now you know how to obtain the two open sets, one containing X and other covering F. How to obtain, you have just seen in the diagram in the earlier proof, but that theoretical part we are to cover now. So since F is closed, and X does not belong to F, therefore X cannot be a limit point of F. It cannot be a limit point of F. If it is a limit point of F, then every neighborhood of X will have a non-empty intersection with the set F. But since X is not a limit point of F, there exists a neighborhood, open set you can say, X minus epsilon, X plus epsilon, say equal to G. I'm naming it as G. So X minus epsilon, X plus epsilon is equal to G, say. So there exists a neighborhood of this type. Leave it here. It is just X minus epsilon, X plus epsilon, a neighborhood such that of X, such that actually G I will rename when I will take the neighborhood as X minus epsilon by 3 and X plus epsilon by 3, then I will rename it as G. Now it is just as it is. So it is such that X minus epsilon, X plus epsilon intersection with F is phi, because X is not a limit point of F. Now let G be the open interval X minus epsilon by 3, X plus epsilon by 3, and let H be the union of all open intervals of the type Y minus epsilon by 3, Y plus epsilon by 3, where Y is a member of F. So for every member of F, you just construct this open interval, and every open interval is an open set, so this is an open set, and take their union, and you know that arbitrary union of open sets is an open set, so H is an open set, G is already an open set. So therefore, G and H are open sets. And these are not only open sets, but these are open sets such that X is in G and F is covered by H. And now we claim that G intersection H is phi, and that will be enough to show that the space is regular. Already we have proved in a previous video that is T1. So T1 plus regular will make it as a T3 space. So only thing remain to prove is that G intersection H is phi, and that we will prove by the method of contradiction. Let, if possible, G intersection H not be phi. If it is not phi, then definitely there exists some element Z in G intersection H. So this means Z will be in G as well as Z will be a member of H. And keep in mind that H is the union of open intervals of the type y minus epsilon by 3, y plus epsilon by 3, where y is a point of F. Keep it in mind. It will be working in the next step. Z is in G. What is G? G is your x minus epsilon by 3, x plus epsilon by 3. If Z is a point of this interval, then definitely distance of x and Z is going to be less than epsilon by 3. This is clear. This is x. This is x minus epsilon by 3. This is x plus epsilon by 3. And wherever you take Z, the distance of Z from x cannot be greater than the extreme distance, epsilon by 3. So this distance is always less than epsilon by 3. On the other hand, Z belongs to this union. So if it belongs to this union, definitely it will be in some of the members of this union. So there exists a member to which this Z belongs. And Z belongs to y minus epsilon by 3, y plus epsilon by 3 for some y belonging to F. For some y belonging to F. Now, x minus Z mod is less than y by 3, epsilon by 3, sorry. And Z belongs to this interval also. On the same lines, where we have seen that mod of Z minus x is less than epsilon by 3, from here we can have mod of Z minus y is also less than y by 3. Now, I will use the triangular inequality. So, what the result we will obtain using triangular inequality? This is x minus z, this is z minus y. So, I am going to write that y minus x mod is less than or equal to mod of y minus z plus mod of z minus y. And this is well known trigonometrical inequality. So, y minus z mod, further z minus y mod or y minus z mod is the same thing. So, this is going to be less than epsilon by 3 plus this is again, sorry, it is y minus z, it is z minus x. So, mod of z minus x is again less than epsilon by 3, that means 2 epsilon by 3, and 2 epsilon by 3 is less than epsilon. So, y minus x mod is less than epsilon, which means y belongs to x minus epsilon, x plus epsilon. And y is a point of F. And y is a point of F. That means these two sets have non-empty intersection, which is a contradiction, because in an earlier step you have just written that x minus epsilon, x plus epsilon, open interval intersection with F is phi. If the intersection of these two sets is phi, how y can belong to both of these two sets? So we arrive at a contradiction, and this is a contradiction because we have supposed that G intersection H is not phi. So G intersection H is phi. So that means for every closed set F and for every point x not belonging to F, we have obtained two open sets G and H such that x belongs to G, and H covers F such that G intersection H is phi. That means G and H are disjoint, and that makes the space RU regular. RU is already T1, so regular plus T1 is a T3 space, so RU is a T3 space. This was the first theorem of today, and now there is a similar theorem. Similar theorem means a little bit change in the proof, not too much, and the theorem is prove that every metric space is a T3 space. You can say metric space or you can say topology generated by metric space, it is one and the same thing. Both are T3 spaces. So here I'll prove that every metric space is a T3 space. So how to prove it? To prove it, our starting point is the same. Since we have to prove that it is a T3 space, that means we will have to prove that it is regular as well as T1. T1 we have already proved. We just now require to prove that metric space is a regular space. It is already T1. I will prove it regular. So regular plus T1 will make it a T3 space. And to prove that the space is regular, from where we are to start? We have to take a closed set and a point that does not belong to that closed set. So let F be a closed subset of metric space and X does not belong to F. X is a point which does not belong to F. If X is not in F, then where X is? X is in the complement of F. So this means X belongs to F complement. Now F is a closed set. That means F complement is a open set. If F complement is open and X belongs to F complement, therefore by the definition of metric spaces, there must exist an open ball centered at X of some radius which contains X and which is a subset of F complement. So therefore there exists an open ball. There exists an open ball BXR such that this X belongs to BXR and BXR is a subset of F complement. Since BXR is a subset of F complement, this clearly means that BXR intersection with F is phi, because BXR is a subset of F complement. So BXR will have no part in F, so its intersection with F will become phi. Now we consider two sets. Now let G be the open ball B X at R by 3. Consider the proof is, I told you earlier that the proof is on the same lines as we have proved the previous theorem. So let G be the open ball centered at X and radius R by 3, and H you know how to construct. Same as you have done in the previous one. You take open ball B by R by 3 where Y is a point of F, and then take union of all those. So Y belongs to F and their union. Since you have taken every point of F and you have constructed an open ball, like situation is like this, that here is your F, and for every point in the set F you have constructed an open ball. You have constructed an open ball for every point. So all points are covered. Every open ball you have taken, and now their union. So definitely the set, this is the set, this is the set. I have darkened a little bit. Up to what extent it is possible, I have darkened it. This is the set F. This is clearly covered by the union of all these open balls. So that means, therefore, then your X belongs to G and your F is covered by H. So G is an open set, H is an open set, G contains X, H contains F. Only thing remains to prove that their intersection is phi. If we can prove that G intersection H is phi, then the metric space will become regular. T1 already it is, so it will become T3 and the proof will be completed. So now we claim that this G intersection H is phi. And the proof is, once again I'm telling you, almost the same. So let Z be a point in G intersection H. So this means Z belongs to G and Z belongs to H. This means Z belongs to the open ball B X R by 3 and Z belongs to union of open balls B Y R by 3 where Y's are the points of F. The proof is the same. The only thing that has been changed here, earlier we were working with the open intervals and now we are working with the open balls. So this means earlier we were talking about the distance as mod of dz by mod of z by z minus y, mod of x minus z. Now since it is open ball and it is a metric space where d is the metric, so from here you will get d of zx is less than r by 3. Earlier you were writing here z minus x. Now it is d of zx. So and similarly, since z belongs to the union, that means z must be at least in the one of these open balls. So z belongs to some open ball b by r by 3 for some y belonging to f. For some y belonging to f, and since z belongs to this open y, once again d of zy is less than r by 3. Y belongs to f is clear because already written as for some y belonging to f. Once again I'll move on to the triangular inequality. So d of xy is less than or equal to d of xz plus d of zy. It is less than r by 3 plus r by 3 is equal to 2r by 3 is strictly less than r. So d of xy is less than r. Now that means y belongs to open ball bxr and y was the point of f. Y is a point of f that belongs to bxr, and earlier you have written that bxr intersection with f is phi. If intersection of these two sets is phi, how a point of f can belong to bxr? So we arrive at a contradiction, and this contradiction will prove that the intersection of the sets G and H is phi. That means you have obtained two open sets G and H, G containing X, H containing the closed set F, and their intersection is phi. That makes the matrix space regular. It was already T1, I have told you twice earlier. So T1 plus regular, that means it is a T3 space. So every metric space is a T3 space. So there are more and more theorems on regular spaces. So I'll take one or two more theorems today. So let us have another theorem on regularity of topological spaces. So prove that homeomorphic image of a regular space is regular. That means actually we want to prove that regularity is a topological property. Regularity is a topological property. That's what we want to prove through this theorem. So I'll move on to the proof now. Let X top be a regular topological space, and Y rho is any topological space topological space and let f from x top to y row be a 1 1 onto continuous open map. This is given to be regular. So this is given to be regular, and what we require to prove that this is also regular. To prove it regular, our starting point will be same. We will take a closed set here and a point x not belonging to that closed set, and then we will try to find two row open sets, G and H, G containing that particular point, H covering that particular closed set, and G intersection H is phi. If we can do this all, then YO will be a regular topological space, and that is the required in the statement. So I'll move on to start the main proof of the theorem. Whatever is given, I have written. So let F be a row closed subset of Y, and let small y, a point of Y, be such that Y does not belong to that closed set. So a closed set is there, a point of the space is there which does not belong to that closed set. Since F is on 2, there exists X in the set X such that F of X is Y. So that means your F of X does not belong to F. F of X does not belong to F directly means that X does not belong to F inverse of F. Now X is a point of X and F is a closed set. The map F is continuous. Here I have written, I have rubbed. It is a continuous map, and you know that continuous inverse image of a closed set is closed. So F inverse F is closed. So this is a tau closed set now. Tau closed subset of X. So you are having a tau closed subset of X and a point of X not belonging to that, and the space X is given to be regular. If in a regular space there is a closed set and there is a point which does not belong to that closed set, then there must exist two open sets G and H, G containing this point, H covering this set, and G intersection H is phi. So therefore there exist tau open sets G and H, tau open sets G and H such that X belongs to G. Your F inverse F is covered by H and G intersection H is phi. Now we are very much near to the proof of this theorem completion. X belongs to G. That means F of X belongs to F of G. F inverse F belongs to is a subset of H. That means F is a subset of F of H. And G intersection H is phi. So that means F of G intersection H is also phi. Now I'm rewriting the step. this fx is y, so y belongs to f of g, f is covered by f of h, and this I can write fg intersection fh is phi. Now look, g and h are tau open sets, and the function f is open map. So f of g is row open, f of h is also row open. So we have obtained two row open sets where we have started with a closed set f, row closed set f, and a point y not belonging to f, and we have obtained two row open sets fg and fh such that y belongs to fg, f is covered by fh, and their intersection is phi. That means we have proved that the topological space y rho is regular. So regularity is a topological property. So this was another important theorem that we covered today, and I'm not going to leave just here before covering another important theorem. So there is another important theorem which I like to cover today. The theorem is regularity. Regularity is a hereditary property. That means if a topological space is regular, then every subspace of that topological space is also regular. So let X top be a regular space, let Y be a subset of X. Consider the subspace Y tau Y. Now you know that how the members of tau Y will look like. Since tau Y is a subspace of tau, so every member will be some member of tau intersected with Y. So that means if there is some member, you can say G dash here in tau Y, then G dash will be G intersection Y, where G will be a member of tau, because tau Y is a subspace of tau. Now what we require to show is that Y tau Y is also regular. So to show that this is regular, we will have to start by taking a closed subset of Y tau Y and a point that does not belong to that closed set. So let F be a tau Y closed subset of Y, and let Y be a point that does not belong to F. Y does not belong to F, but Y is a point of Y. Keep it in mind that Y is a point of Y. Since F is tau Y closed set, therefore there exists tau closed set U such that F is U intersected with Y. So this Y does not belong to F, means Y does not belong to U intersection Y. Y does not belong to U intersection Y, but Y belongs to Y. That means Y does not belong to U. So Y does not belong to U. What is U? U is tau closed set. This is a tau closed set. A tau closed set at a point that does not belong to that, but X tau is given to be regular. So by regularity property, there must be two tau open sets G and H. So there must exist. So therefore, there must exist tau open sets G and H such that your Y is in G, comma, your U is covered by H and G intersection H is phi. Now, Y belongs to G, Y also belongs to Y. From these two, I can say that Y belongs to G intersection Y. Okay, U is a subset of H. This means U intersection Y is a subset of H intersection Y. And since G intersection H is phi, intersection with Y will also be phi. Phi intersected with any set is phi. And now, almost the final step of this theorem. Y belongs to G intersection Y. G intersection Y, I call it as G dash. G is tau open. Any tau open set intersected with Y will become tau Y open set. So G dash is tau Y open set. This is a tau Y open set and Y belongs to this. This U intersection Y, earlier you have seen this is F. So F is a subset of H intersection Y. Once again, H is your tau open set and tau open set intersection with Y is tau Y open set. So I rename it as H dash. So H dash is tau Y open. Y belongs to a tau Y open set. F is covered by a tau Y open set and this condition G intersection H intersection Y, I can write G intersection Y intersection H intersection Y is phi. But what is G intersection Y is G dash and it is H dash is phi. So for closed set F, tau Y closed set F and Y not belonging to F, you have obtained two tau Y open sets G dash and H dash such that G dash contains F, H dash contains F and their intersection is phi. That makes the subspace Y to Y as a regular space. So here I am going to stop today. In the next video, we will have more and more theorems on separation axioms. Till then, thank you once again.